everyone. My name is Alexey Potapov, and my talk is about real-time genetic algorithm-based probabilistic programming in application to robot control. So, why probabilistic programming? Let me refer to the previous speaker and say that this framework has some functional elegance in terms it allows us to use the same inference engine to do perception, reasoning, learning, and so on. So actually, probabilistic programming is in some sense similar to graphical models, but it is more general. So graphical models don't allow us to represent arbitrary regularities, arbitrary models, but probabilistic programming does allow us to do this. And for example, it is quite easy to implement some kind of Solomonov induction in probabilistic programming. Actually, you even don't need to know about Solomonov induction to do this in probabilistic programming. You simply write a generative model generating arbitrary programs, and you will write this program in such a way that it will induce universal prior probabilities. So it's a very good thing, I think. But of course, it has some cost, and this cost is computational inefficiency, of course. And of course, we should have solutions which can work in the conditions of limited computational resources and knowledge and so on. And again, when we implement some models in a probabilistic programming languages, we immediately see if they are applicable to some real-world situations or not. So instead of writing down some equations, we write programs and run them. So I think that probabilistic programming in this sense is a very good framework which can help us bring together both cognitive architectures and universal induction. But of course, it's only a way to set the problem, not to solve it. Well, today I will not go to speak about universal induction, but I will speak about one particular limitation of traditional probabilistic programming languages. Namely, they don't allow us to manage resources. And if we are trying to use probabilistic programming languages, for example, for such tasks as robot navigation or robot control, then it would be quite difficult. So if we use probabilistic programming languages, then we can relatively easily solve the problem of planning. Well, of course, if we have enough resources, but this is another question which we study in other papers. Okay, but usually robotic control is carried out using not only planning but also reactive control. Everyone uses something like hierarchical task networks and so on. So if we want our framework to be general enough to be applicable in real AGI agents, then it should be able to deal with both planning and reactive control, or to perform replanning while executing plans faced with unexpected conditions because we don't know full information a priori and so on. Okay, so we have we don't have cognitive architecture right now, but we have several experimental implementations of different probabilistic programming languages, and one such implementation is based on C++, and it's very simple in some sense. There is a special random number generator which remembers random choices which were made, and we simply need to write a fitness function which uses this random number generator for those variables which values should be optimized. Well, I have not said yet that we use optimization queries instead of sampling, but this is a particular question. Okay, so you can write something like this, call genetic algorithms to optimize it, and it will work. So you write plain C++ code instead, except the fact that you use a special random number generator. Okay, so how can planning problem be solved in such a framework? We write a generative model for a plan. For example, it samples a number of steps in the plan from some uniform distribution. Then each step of the plan contains some action which is sampled from a multinomial distribution. These actions are directly mapped to the actions of our robot. In our case, we used now robot, and we can use some actions which are previewed in this SDK of this robot. Each action has some free parameters which are also unknown a priori, and we sample them from some distributions, and that's all. Here we have a generative model for a plan. Then we need to calculate a fitness function, how this plan good or not. So we should have some environment model. In the probabilistic programming framework, of course, you can also learn this model, but this is a more difficult question, and we should have something like cognitive architecture already to do this stuff. So we, in our current work, we think that the environment model is given. So we use very simple environment model. We can use something like physical simulations, but we don't need it in our case. Robot has some sensors like sonars and sensors which give us odometry data. So the goal for the robot is to move to a specific location. Actually, we can use any kind of goal which is expressible in these narrow settings. So, for example, a robot may have a goal to avoid some object or something else. So we don't need to hard code some rules for the robot that it should stand up before walking, it should avoid obstacles and so on. This is absolutely not necessary, because it generates a random plan, it evaluates, it simulates its execution and evaluates its result, and sees how the result is different from the goal. And genetic algorithms optimize parameters of this plan, and we have such plan. Okay, so for example, here is an initial robot position. It has a goal to go here. Here is a found plan which contains standing up and avoiding an obstacle. So we didn't program our robot to stand up especially for working and so on. So this is a good think about it. And yes, it's successfully achieves its goal. But if we will try to execute our plan blindly, without taking into account new information and so on. Actually, when the now robot tries to stand up, it randomly changes its orientation. So if we blindly execute our plan, its execution will be imprecise, at least because of this. But there are many other problems. Some unexpected obstacles, moving objects can appear in front of this robot and so on. So we need to perform some kind of replanning. Our idea was to perform plan optimization and its execution simultaneously. So we run well, we used a very simple hack. We simply use a fork to separate genetic algorithm-based optimization of plans with others written, which we execute this plan, and we run our genetic algorithms, say, for half a second. Genetic algorithms continue to run. We take the current best plan and start to execute it. And while genetic algorithms are optimizing the fitness function, this fitness function simply changes because circumstances are changed. And a population of candidate solutions can follow the shifts of the maximum of this fitness function. So the plan, which is found by genetic algorithms, it's permanently updated and adjusted. So, well, there are some technical questions regarding how to simulate a partially executed plan. It's not a big problem, but it should be taken into account, because when we already executed a part of plan, then, well, in order to not considerably change our fitness function just because we already executed a part of plan, we need to take it into account and to skip the part of plan which was already executed. So we performed some experiments and found out that it really works. A robot was well, there were small heuristics such as when the value of the fitness function of the best candidate solution is changed considerably, the robot waits for half of a second in order for genetic algorithms to find a better candidate solution. We switch to another plan, not every time when we're able to find some better plan, but only better for a certain threshold than the fitness function of the plan which is being executed, and so on. Okay, well, in general, it works. I would not lie, it works not so perfect, just because at least we have some limitations in what a robot can feel. For example, we use sonars just to estimate the distance to the obstacle in front of the robot, but we don't know precise coordinates of this obstacle, so the robot may try to choose a very long path around this obstacle or something like this. But in general, it works quite well. It helps to improve accuracy of the results of the plan execution. So if we use prior plan without replanning and adjustments, then when a robot works for a goal which is located in a meter or two, it can make mistakes about 20 centimeters. But when we introduce new information during planning and genetic algorithm-based optimization, errors are much less. They're about 10 centimeters. It also indeed can avoid new or preliminarily unknown obstacles. Okay, so in general, it's quite possible to use probabilistic programming approach in the robot control, and as far as I know, it was done for the first time in such settings. So we believe that in general it's quite a good framework to practice procedure further. It's a very general framework. Of course, there are many difficulties with efficiency, so here we used quite a simple search space, but if we are going to use algorithmically complete program space, then of course existing probabilistic programming languages based on sampling techniques or based on genetic programming techniques will not make a miracle and solve these problems efficiently. But well, it's quite a good framework to state these problems, to look at them, and to try to solve them in practice. So thank you.